This video is still in the chapter of linear dependence and linear independence. In the previous video we checked if these functions were linearly dependent or not in this vector space, where the vector space was functions taking from the reals to the reals. And in this video we are going to do more or less the same with different functions. So let us say we have different functions. Sine of t, g of t, we are going to use cosine of t, and h of t, let's use a polynomial like t. Okay, let us check if they are linearly independent. Okay, so for that to happen, we need f plus g plus h should be 0 if and only if x, y, and z are 0, where x, y, and z are scalars. Okay, so that is x sine of t plus y cosine of t plus z times t, right? So they will be linearly independent if and only if x is 0, y is 0, and z is 0. Okay. So we have three functions. We have three scalars here. So let us pick t at three different values. Let us say t0, t. We have some trigonometry here, right? So let us use something like pi over 2 and pi. Okay, so that will be for f of 0, right? So here the functions will be of 0. So we will have x sine of 0 plus y cosine of 0, right, plus z t of 0. Okay, and that has to be 0. Now, okay, so then x sine of pi over 2 plus y cosine pi over 2 plus z pi over 2 equals 0, and x times sine of pi plus y cosine of pi and z pi equal 0. Okay, so this is more or less the same as we did before, right? So sine of 0, that will be 0, right? Here cosine of 0, that will be 1, right? And z of 0, so that's 0, right? Okay, so this is basic trigonometry, right? So what we are getting here is if x is times 0, so we can erase this, y times 1, z times 0, so okay, we have a result here, x times 1, this 1 we can erase 2, so we have z pi over 2 equals 0, x times 0 here, this will be minus y, and this will be z pi equals 0. Okay, now so y should be 0. Now if y is 0, z pi equals 0, that means z is 0, right? And if z is 0 here, x has to be 0. Okay, so f, g, and h, the three functions, they are clearly independent. Well, but there is another method to do this, to check if functions f, g, and h, if they are linearly independent. And this other method is a bit more complicated, so if you are impatient and you don't like this sort of method, please turn the video off now. But I'm going to show to the other viewers, because this method in some fields of mathematics, they are really handy. The idea obviously is still the same, right? So we have to see if there is a way of this being 0 without x being 0, y being 0, and z being 0. In the previous method, at the end of the day, what we did was we took 3 positions for the functions, right? We took one position, f of 0, g of 0, h of 0, then we took f of pi over 2, g of pi over 2, h of pi over 2, and f of pi, g of pi, h of pi, right? The good thing about this method is that we are not going to use this, okay? We are not going to use this, and we are going to take the derivatives, okay? So I'm going to erase this, and I'm going to show it. Okay, so we have x sine of t, y cosine of t, z of t. We take derivatives. Okay, so we do so the functions are f, h. So we do d f of t. Okay, so we take the derivative in order to t. Okay, so this will be x cosine of t. So x is a scalar, do not forget that, right? So here, this is taking this basic derivatives, and with respect to t, the derivative here is 1, so we have z, right? That will be 0, and you take the derivative again, right? So we are going to get minus x sine of t, y cosine of t, and the derivative here is 0, right? And you take the derivative again, so we have minus x cosine of t, so the derivative here is plus, right? So sine of t equal 0. Okay, so this is the original one, right? Okay, and here we have 3 derivatives. First derivative, second derivative, and third derivative with respect to t, the variable. Okay, so I have this line 1, 2, 3. So if I add 1 plus 3, so this and this, they will cancel, this and this will cancel, we will get z equal 0. Okay, so we already have one value for the scalars. So now in lines 2 and 3 we have minus x sine of t minus y cosine of t, right? And in line 3 minus x cosine of t plus y sine of t. What I'm going to do now is I'm going to multiply all the second line by sine of t, okay, and this one sine of t too, okay, but times 0, that will be 0, okay, and the third one I'm going to multiply by cosine of t, okay, cosine of t, but times 0, that will be 0. Okay, so I'm going to erase this. This is ridiculous. Okay, now we have so what we have here is the squared, right? Squared. Here the same, squared. And wait a sec. No. I'm making mistakes here. Here I have a squared, that's correct. But here I don't have a squared. Okay. Here I have a squared, but here I don't, right? Okay. Yes, now it's correct. Now what I'm going to do is, I think there is no mistake here now, I'm going to add them. Okay, so I will get minus x sine squared t plus cosine squared of t, and here I will get a 0, right? So okay, so this is 1, so we have minus x times 1, because this is 1, right, equals 0, so that means that x equals 0. Okay, so we have z equal 0 and x equal 0. Okay, well, you have lots of ways to finish this off, right? Because knowing that z is 0 and knowing that x is 0, you come, for instance, here. Now z is 0, right, and x is 0, so this one will be 0 only if, well, if y is 0, right? But you can do the same process as I did here. Okay, I multiplied all this by the cosine and all this by the sine, all this by the sine, this one, second line, and all this by the cosine, right? And now you can repeat the process for those two lines, and you will get y equals 0. So x is 0, y is 0, z is 0. So the only way of this system here, not the system, this equation here, to be 0 is if x is 0, y is 0, and z is 0. So the functions, as we have seen in the previous method, are linearly independent. So I warned you about this method, okay?